Here's a thought experiment. Imagine you have a team of hundreds of experts, engineers, doctors, lawyers, historians, mathematicians, etc. You give them a problem. Do you really think you need hundred of experts simultaneously to think about that problem? Of course not. You will route that problem to two or three relevant experts. That is exactly what mixture of experts does for language models. Hello everyone, welcome back. Today we are going to understand what is mixture of expert, why it exists, how it works, and how it enables the models like ChatGPT-4 and Mixtral to have billions of parameters while still running efficiently. So let's first understand the scaling problem. In a standard dense transformer, more parameters equals to more compute. If you double the parameters, you roughly double the compute per token as well. This creates a problem at some point. Like, you can't afford to run the model. GPT-3 has 175 billion parameters. Running it requires enormous compute for every single token. Think of it like scaling it to 500 billion or 1 trillion parameter itself. Even more expensive it will become. So mixture of experts breaks this link between model and size compute. In mixture of expert model, you have 1 trillion total parameters, but only activate say 10 billion of them for any given token. The rest are idle. More knowledge, like more expert, without proportionally more compute. This is fundamental appeal of the mixture of experts. So now let's discuss how mixture of expert actually works. In a standard transformer, each layer has one feed forward neural network that every token passes through. In MOE or mixture of expert transformer, that single feed forward network or neural network is replaced by with n experts like feed forward neural networks, typically 8, 16, 64 or even more. And a small router network that decides which expert each token goes to. The routing process goes like this. Like first token arrives at MOE layer with hidden state H. Then router computes score with score equal to softmax of H into the weight of the router. This gives a vector of n scores. Then you select the top k experts, typically k is equals to 2. Then you route the token to those k experts. Then each expert processes the token independently. You combine expert output weighted by router scores, and you finally continue to the next layer. So if you have 64 experts and k is equals to 2, each token only activates 2 experts per MOE layer or mixture of experts layer. The other 62 do nothing to this for this token. The capacity factor is like if all token rushes to the same popular experts, those experts become overload. So unpopular experts sit idle. So a capacity factor sets a maximum number of token each expert can process per batch. Tokens that exceed this cap are dropped or sent to backup experts. This creates a tension. Like we want balanced expert utilization, but we also want each token to go to its most relevant expert. These goals conflict. So to resolve this, we have something load balancing or expert routing strategies. So the biggest challenge in MOE training is making experts specialize without causing load imbalance. Sorry. Without any intervention, router tends to converge to always picking the same few experts as we discussed. Those experts get the most training signal. They get better. The router picks them more often. Eventually, most experts are never used. This is called expert collapse. And to fix this, we add an extra loss term that penalizes imbalance. If the router picks expert 1 for 80% of the tokens, it get penalized. This encourages more uniform routing. But the downside is it interferes with the router learning to make semantically meaningful routing decisions. So instead, we have a third option for this, that is expert choice routing. Instead of tokens choosing experts, let experts choose tokens. Each expert picks its top k tokens from the batch, and this guarantees perfect load balance by construction. So the trade-off here is like a different token may be processed different by different number of experts and complicating implementation. So when an expert is at capacity, extra tokens are skipped, dropped at that particular layer. They continue to the next layer without being processed by an expert at the current layer. This can hurt quality for long sequences where dropping is common, but works well in practice with a reasonably capacity factor. So we have few models that have implemented this like MOE architecture or technique. We have a Mixtral 8 cross 70 billion parameter that was released in 2023. It has 8 experts per MOE layer, and the K value is 2 like activated per token. Total parameters are 47 billion parameters, and active parameters per token are around 13 billion. And it has the inference cost similar to a 13 billion dense model, and the quality comparable to 70 billion dense model. So and it has open weight, so it's downloadable and runnable. The second one is the DeepSeek MOE. So DeepSeek pushed MOE or mixture of experts further with the two innovations. First one is like fine-grained experts. Instead of 8 large experts, you use many small experts like 64 or 256. More granular routing, better specialization. And the second innovation was shared experts. You reserve k number of experts that are always activated for every token. These handle common knowledge that all tokens need, and remaining experts are routed normally. Results for this approach is like better quality at the same active parameter budget. And finally, it is rumored, but GPT-4 like also uses some form of MOE architecture. OpenAI has not officially confirmed, but industry consensus is that GPT-4 uses a MOE architecture with roughly around 8 experts, giving it massive total capacity while keeping inference manageable. So I would not consider GPT-4 MOE architecture, but yeah, it is rumored. Okay, so the next one we are going to discuss is tensor parallelism or model parallelism. MOE models are massive, so you need multiple GPUs to hold them. Let's understand how to split models across GPUs. So this is what a tensor parallelism solves. You split each weight matrix across GPUs along one dimension. For one linear layer, W of shape, let's say 4096, 16384. GPU 0 will have columns 0 to 4095, and we call it W naught weight. GPU 1 will have columns 4096 to 8191, we call it W1. So on and so forth, GPU 2 and GPU 3. Each GPU computes its partial output. and all reduce operations sums them up. The communication across all reduce after each layer with NVLink that has around 90 GB per second. This is fast over PCIe that is around 64 GB per second. But it becomes a bottleneck as because of the speed difference. So the second technique we have is pipeline parallelism. You split layers across GPUs in not as per the columns but as per the layers, like GPU 0 layer 1 to 20, GPU 1 layer 21 to 40, and so on and so forth. So activations passes from GPU 0 to GPU 1 to GPU 2 to GPU 3 and so on. This reduces communication, like only activations pass between stages, not waits, but introduces pipeline bubbles. GPUs waiting for the previous stage to finish. So to handle this, there is one more technique called expert parallelism. For MOE models specifically, each GPU holds a subset of experts. Again, to give you an example, like GPU 0 will hold experts 0 to 15, GPU 1 will hold experts 16 to 31, and so on and so forth. When the router selects expert 35 for a token, that token's hidden state gets sent to GPU 2 because GPU 2 was having experts from 32 to 47, and it is processed and sent back. This requires all-to-all communication, like every GPU potentially communicate with every other GPU. So MOE is one of the most important architectural innovation in modern LLMs. It solves the fundamental tension between model capability, like need more parameters, and inference cost, like need fewer active parameters. The real world implementation, as I discussed, are Mixtral, DeepSeek, and rumored GPT-4, shows that MOE works at scale. The challenge of load balancing and expert parallelism are engineering problem that the field is actively solving, or the experts are looking into, researchers are looking into. So in the next video, we will discuss multimodal inference, like what happens when you show an LLM an image with the text as well. Thanks for watching. See you next time.